Have you ever wondered what lies beyond our world and how it all works? A pleasant day and dangal greetings. I, along with my groupmates from Group 1 of 1ECE-A, will guide you through the fascinating field of astrophysics. What if the universe's biggest mysteries are written in the stars? Astrophysics uncovers them. In this presentation, we'll cover its origins, discoveries, concepts, equations, applications, and challenges. Now, let's dive deeper into astrophysics and discover why it's more important than ever.
Thousands of years ago, the Babylonians, Indians, and Chinese used stars to track time and seasons. The Greek took it further, asking why things move the way they do. Some thought Earth was the center, but then Copernicus came, who flipped the idea, putting the sun in the middle. Kepler and Galileo gave us proof, and Newton's law explained it all with gravity. Tools got better, so did our question. We started seeing invisible light like infrared and noticed hidden patterns in starlight. That's when astronomy became measuring and understanding. Einstein theories reshaped space and time, Hubble showed the universe is expanding, and even discovered black holes, dark matter, and even heard gravitational waves.
Astrophysics explores how the universe works. Gravity moves galaxies, radiation helps us see space, and stars shine through nuclear fusion. Thermodynamics drives star life, and relativity explain black holes. We study stars, galaxies, planets, nebulae, and redshift, which shows the universe keeps expanding. Next is astrophysics follows big theories like the Big Bang, stellar evolution, relativity, quantum mechanics, and cosmic inflation. We study space using tools like photometry for brightness, spectroscopy for elements, astrometry for positions, interferometry for detail, and timing to track changes.
This image shows Hubble's law, which proves the universe is expanding. The x-axis represents distance and the y-axis represents redshift, which tell us how fast galaxies are moving away. The farther a galaxy is, the more its light is stretched toward red, meaning it's moving away faster. This follows the equation B is equal to h naught times d. This is Kepler's third law, also known as the law of harmonies. It states that the square of a planet's orbital period is directly proportional to the cube of the orbit's semi-major axis. As shown in the picture, t squared is proportional to a cube, where t is the period and a is the average distance of the planet from the sun. This helps us predict how long a planet takes to revolve based on its distance.
The first mechanism, cosmic ray acceleration, occurs when shock waves from supernova fragments accelerate particles that cross the shock front to gain energy until they escape into space. Next one involves neutrinos, where high-energy cosmic rays collide with matter, creating pions that decay into neutrinos, which then carry crucial information about distant astrophysical processes. The third one explains black hole formation. When a massive star collapses under gravity, the core forms a black hole, while outer layers are expelled in an explosion. Next, gravitational waves, which are produced when massive objects like black holes or neutron stars merge. These waves propagate through space-time, and we can detect them all throughout.
Moving on to the unresolved questions in astrophysics. What is dark matter and dark energy? Making up 95% of the universe, but we don't know what they are. Are we alone in the universe? Other intelligent life should be common, but we haven't found any signs yet. How did galaxies and large-scale structures form? The exact process and timing behind structure formation from the Big Bang are still not fully understood. Now onto the field limitations of astrophysics. Limited observational access. We can only see within the observable universe. Inability to recreate extreme conditions. We rely on theoretical models because we can recreate extreme conditions. Lack of a unified theory, quantum gravity. A quantum theory of gravity is needed to understand extreme environments.
Space tools like infrared thermometers used to detect heat in space are now used for medical temperature checks. Anti-scratch lens from astronaut helmet are now eyeglasses in smartphones. Water filtration system developed from space are used to disaster relief in homes. Image processing algorithms from space data are now using CT scans and facial recognition. Robotic arms from space exploring assist in surgery. Cryogenic tech from space keep MRI machine and supercomputer running efficiently.
Astrophysics explores the universe, how it began, what it's made of, and how it evolves. It dives into phenomena like black holes, dark matter, and the forces shaping everything. By blending physics with astronomy, astrophysics helps us understand the cosmos, from massive galaxies down to invisible particles. The discoveries in astrophysics don't just stay in textbooks, they drive scientific innovation. Concepts like relativity, proven through astrophysical studies, are now essential in satellites and spacecraft systems. From precise atomic clocks to advanced communication tools, astrophysics continue to inspire breakthroughs in technology, engineering, and how we measure time. You might not realize it, but astrophysics is part of your everyday life. GPS wouldn't work without time correction based on relativity. MRI scans come from technologies used to observe space magnetism, and Wi-Fi that came from radio astronomy, detecting signal from deep space. These practical tools are here today because of humanity's quest to understand the stars.
Here are some of the challenges that we might face. First is the observational limits. Distant objects and phenomena are difficult to observe directly. Another is the interdisciplinary barriers. The integration with quantum physics, particle physics, and cosmology remains complex until today. Future prospects are the next generation telescope, upcoming missions like the new Nancy Grace Roman Space Telescope, AI and machine learning, enhancing pattern recognition in large dataset. Lastly is the exoplanet studies, improved chances of detecting Earth-like planets and biosignatures. Astrophysics remains as one of the most captivating and challenging fields in modern science, driving our quest to understand the universe's deepest mysteries. Experiencing obstacles such as the observational limitations, the field not only expands our scientific knowledge but also enriches our perspective on the universe we live on.